Okay.
Yeah.
So can I start now?
Yeah, please do.
Okay. So thank you, Carol, for organizing this series, first of all. So my name is Yasufumi. I'm based in DCU. And today the topic of my presentation is multimedia automatic speech recognition for multimedia search. So this is based on my PhD project, and I'm supervised by Gareth Jones. So first, here is an overview of my presentation. So first, I will go into introduction. There are two topics here. So searching for speech documents, and the second one is automatic speech recognition. So when searching for speech documents, it is very important to have a automatic speech transcripts. And for that, to generate speech transcripts, ASR, automatic speech recognition, is normally used. So I'm going to talk about both of these systems. Then moving on to the background, here I'm going to explain briefly how ASR system is composed, and then talking about the issues with the ASR. So even the best ASR systems still have an issue these days. Then the third topic is potential solutions to the issues I was going to talk about in the background section. The first approach is using multimodality. So the system is not only relying on acoustics, but also on visual features. Like thinking about how humans interpret, understand the speech, we also take visual information. So that sounds natural approach. And then the second approach is exploitation of external resources. So ASR is built on it's basically an extension of ASR systems using something like Wikipedia corpus or a knowledge graph, and to make the system better. And then the final section is a conclusion. So first, searching for online text document is relatively easy. So because we have Google, and if we type ADAPT Center in the text box, and then we can get the list of pages. Or we can do Control F to find the words in the page, web page. That is also easy to do. So what we need to do to find the text document is enter a query expressing the information you need and match the query to the document, and then you get the output, what you want to find there. However, when it comes to a spoken document, multimedia speech documents, it is much harder. So first of all, the contents of the documents are generally available, but not always. And when we think about the new services such as YouTube or podcast, like there is a number of podcast channels on Spotify. And now because of coronavirus, the universities are moving on to the online lectures. So there are many archives of multimedia data, and it's getting bigger and bigger. So users can look for specific content based on titles or metadata, but this is a very limited functionality. When we think about multimedia speech documents, maybe we want to find a specific region, like from minute 3 to minute 4, or when the Irish president said, talked about the corona in his press conference or something like that. So I found this video online, and the top title is Don't Learn Machine Learning. It's a very provocative topic. And this is like 18 minutes, but I don't want to look at the whole length of the document here. And there are like 1 out of 10 people disliked. So I just want to know why he thinks it's a bad idea to learn machine learning. So I only want to see maybe like 30 seconds of the important, the core topic of this video. So for that thing, more sophisticated functionality of a search system, that's nice to have. And for to search for speech documents, we often use automatic speech recognition. This is a handy system because it can transcribe speech into text. So now you can run Control F here. But even the best ASR built by Google can make errors in word transcription. So we can look at this video. So here's a rugby match Ireland against New Zealand. And the commentary is talking, but I turned on the old caption, but it doesn't recognize words at all. One reason is the crowd audience, like they are very loud in background. Plus, there is a background music, so that probably prevents the system from recognize anything. So, okay, and I'm going to move on to the ASR architecture here. So here's a ASR, very general architecture, simplified one. So the input is a waveform, which is like this kind of a wave-shaped speech. And this is a real number, a sequence of real numbers. So something like 42, 43, 50, 70, 80, and then going down 70, 50, and so on. But this is not the convenient format for ASR to recognize. So what people normally do is taking the 5 seconds of a waveform, let's say, and then these 5 seconds of speech digits are now converted into a vector, one vector, and doing this through the waveform till the end. So from 0 second to 5 second, 5 second to 10 second, 10 second to 15 second, and then we get a sequence of vectors. And this is going to be an input of an acoustic model, which is a top middle. And this model, what this model does is translating vectors into phonemes. Phonemes is the like smallest unit of a speech. So when we think about the word like cat, there are 3 phonemes. First is k, and the second is vowel a, and the last is a t, cat. So what we need, the second component is a pronunciation lexicon, which is bottom left. So what this dictionary does is translating a phoneme I, A-Y, into I as a word, or it can translate love, L-A-H-V, to love, actual word, and also dog, D-A-O-G, to a dog. Okay, so now we have a translation system from phonemes, the smallest unit of speech, to words, but we also want to have a language model, which is the third component. That's bottom right. What it does is this is built on actual text, and it learns the probability of the words. So here we have a I love dogs, and also it can go to I like dogs too. But the probability of love is higher, so maybe this model was trained on the text in which love occurred more than like. So the system is likely to recognize love more than like. Combining all of these things together, the process is called decode. And then finally, we can get the output string, I like dogs. So that's a basic architecture of an ASR system. And of course, as any AI community does, this one, ASR systems recently adopted more and more neural systems. So acoustic model can be replaced with one big neural network. Language model can be replaced with a neural network. So there are more sophisticated ways to improve the system these days. Okay, so when it comes to the issues with ASR systems, we just watched the video about the rugby commentary, but in general, audio noise such as outdoor recordings or microphone quality can be bad, or audio quality, so telephone speech is more difficult to recognize than usual speech. And speech type is also tricky. because accent. So for example, I speak a Japanese accent in English, and children. So normally ASR systems are built on adult speech, so they have a hard time recognizing child speech. Voiceover, laughing, acting, like these are humans can change the tone of speech or some burst of a noise, and these are also causing the problems as well. And crosstalk, when 2 or 3 people talking at the same time, the system also cannot handle that kind of speech well. The final issue is out of vocabulary words, which is called the OOV words. And this is basically the ASR systems have a finite vocabulary. So when we think about the pronunciation lexicon in the previous diagram, there are only I like dogs, but when someone says cat, it can recognize cats because it's not in the vocabulary. So that's another issue. Here's a potential solution using a multimodality, and this is a motivation. It's fun to watch. So some of you might have known this effect. It's called a McGurk effect. So in that video, the sound was the same all the time, but just the picture of the man speaking was changed, and he was saying ba, but when the picture was changed, even though the sound was saying, we hear another sound. And this was a motivation to build a audio-visual speech recognition, which tries to integrate the lip movement on top of acoustic speech input. And the goal is to try to make the system more robust to noise, because it can take a lip movement as input. So theoretically, and in practice, yes, that makes the system more robust. More recently, we started looking into more visual context. So when we think about this man holding some tools in the park, there are some context of we can guess what kind of topic he's talking about here. And there could be information like speaker face, which shows that this is a man, what he's holding, the tool, or recording conditions. It's outside, so it's more likely to be noisy than indoor recordings. We have done some work on this topic. So the first one is a speaker face for acoustic modeling. So we integrate speaker face into acoustic model, which we saw in the previous diagram. Also, another one is taking the whole visual picture into a language model and providing the model with more context over what is kind of a thing is spoken there. And there are references here. Of course, these models, these approaches didn't solve all the issues about noise. But one interesting thing was the ASR system learns when male speaker is input for acoustic model, then it does actually expect a male speech. So when female face is input, and but actual speech is a male, then it gives a much higher error. So it does learn like some implicit connection between the male face and the male speech. And okay, the next potential approach is using external resources. And as I talked earlier, ASR systems have a fixed predefined vocabulary. Words not in this vocabulary are referred to as out of vocabulary. And this is a big problem for a search system. So if the user wants to find a document about the coronavirus, but the ASR doesn't cannot transcribe coronavirus because it's not in the vocabulary. And then there's a problem. So it will never find out documents about coronavirus, speech documents. So one potential solution is using an external resource, such as Wikipedia or knowledge graph. So here's an example. This transcript, the Japanese car company Masters brand new. So this Masters is a wrong word, misrecognized word. But still we know that the topic is a car. So we can consult Wikipedia or the knowledge graph, which has a structured, more structured representation of entities. So here, car inventor is connected to car events. So we have more connection with cars here. And this Masters was actually a Mazda. So it's a Japanese brand. And these words, yeah, sound similar, but because Mazda wasn't in the vocabulary, so the system couldn't recognize it at all. Okay. And we have done work on that too. So in the top mid, we have a collection of multimedia documents. First pass is the first transcription of an ASR. So we did a transcribing. We first transcribed documents. Then taking some keywords, based on those keywords, consult a knowledge graph and find the OOVs, out of vocabulary words, which must be relevant to the documents. Adding these key OOVs, out of vocabulary words, to ASR system, and then transcribe the same document collection again. So we have a second pass transcripts, which is top left. And this work was submitted to Interspeech this year. Okay, so going to a conclusion. So there is a growing demand for multimedia search systems because there are more and more services which collect bigger size of multimedia data. Speech transcripts are very important to run, not only just finding speech multimedia content based on titles or metadata, but we want to find like specific segments of multimedia content. As we saw, ASR systems are still not perfect. Like they have a problem with noise, bigger noise, background music, and so on. One potential solution here is fusing multimodal information. So something like visual modality to ASR. The other solution we discussed was external resources. So ASRs have a problem with out of vocabulary, but if we can add some unknown words to ASR, that would be helpful. And in future work, we are planning to, so in the previous work, we only used the knowledge graph, but we are planning to extend this to use Wikipedia as well. And combining together, maybe it's going to be a better solution. The other planning work is, the work planned is running a search task on multimedia data to investigate augmented ASR transcripts to improve search effectiveness. So actually what we does to improve ASR, does it really improve search or not? And that's all from my presentation. Thank you for your attention.